Okay, hello everyone. Today webinar is gonna present jointly with our collaborator from Florida Institute of Technology, Professor Sayed Morshid, and myself, Ahmed Atiyah from Optiwave. The webinar would be about simplified PAM4 signal generation and transmission. We're gonna jointly talk about the PAM background and PAM4 signal generation. And the novel PAM4 signal generation schemes. And then we talk about the experimental setup and results, numerical simulations, and then we end up with the question and answers. And now I'm gonna transfer the presentation to Professor Sayed.
Okay, thank you very much, Ahmad. I appreciate that. So, as my collaborator mentioned, that we will go and talk about the PAM4 background and talk about PAM4 signaling scheme, and especially a novel scheme that we have developed at Florida Institute of Technology to use PAM4 without using a Mach-Zehnder modulator. But before we go there, the first and foremost thing is, why do we need a PAM4 signaling? So the fact is that every day the demand for data is increasing. The demand for data is increasing at a roughly 2 dB per year. That means in about 20 years, we need about 10,000 times more data capacity. And it is almost impossible to lay down that amount of bandwidth in the ground to enable that kind of a bandwidth capacity and to fulfill that requirement. So we have to look at every possible way to increase the data capacity. And with that, one of the ways is the PAM4. And the basic reason we are opting for PAM4 is that right now electronics is roughly at a limit of about 50 gigabits per second over a single channel. So how do you transmit more than 50 gigabits per second over a single channel? That is the key question. So either you increase the data rate by instead of going from 50 gigabit to 100 gigabits per second, or you find some ways to transmit higher bits per symbol. So PAM4 is a technique that allows you to use a lower data rate, let us say 25 gigabit or 50 gigabit, but instead of transmitting only 1 bit per symbol, transmit more than 1 bit per symbol. So with PAM4, you get 2 bits per symbol. If we are operating at 25 gigabits, you get 50 gigabit total ultimate throughput. And if you are using 50 gigabit per channel, and then on top of that, if you added PAM4 signal scheme, then you are able to generate 100 gigabits per lane. So with that, we will talk about a novel PAM4 generation scheme, and that uses a different architecture as opposed to the standard Mach-Zehnder modulator. We will talk about some experimental results that we have at 25 gigabits per second, and that allows you to get data at up to 50, or rather 25 gigabaud per second, that allows us to give at around 50 gigabits per second. And then I'll pass it over to my colleague. He will talk about some numerical solutions, and as mentioned, we will talk about some of the QAs. So there are many different modulation schemes, as we talked earlier. The possibilities are two. Either we send a single bit per second stream, or we have some kind of a coding scheme that allows more than 1 bit per second. These are the two options we have. If you want to increase the throughput, you want to have more than 1 bit per second. Commonly used single bit per symbol schemes include phase shift keying, okay, then we have frequency shift keying, and we have in digital domain, or pure digital domain I should say, we have the NRZ or RZ. At the beginning, we used to use the return to zero scheme, that you get a 1, get back to 0, back to 1, but the efficiency of a non-return to 0 scheme was better. So nowadays we are using the NRZ scheme. All of these on the left side of the screen that you see, these are the single bits per symbol. On the contrary, we could also go for something like QAM, quadrature amplitude modulation, and then 8 QAM, okay, which are different phases and amplitudes combined together to have more than 1 bit per symbol or 2 bits per symbol roughly, okay. And they have some complexities that you have to modulate both the amplitude and phase. So the easiest technique to implement is, especially at optical frequencies where we do not have enough signal processing available to us, because only because of the speed is so high, how could you go do all the other signal processing at that data rate and still be available or still be able to synchronize yourself with the serial data rate? So the easiest possibility is having the PAM4, the pulse amplitude modulation. If you look at it, it is basically very similar to the NRZ scheme on the left. The only difference is instead of having a binary level, 2 level, here there are 4 levels. If I have 4 levels, 2 to the power 2 equals 4 levels, that allows me to have 2 bits per symbol, and that is what the PAM4 exploits. So if you are operating at 25 gigabits per second baud rate, you will be able to get 50 gigabits per second signal over there or data rate. So 2 bits per symbol, that is the basic advantage of the PAM4 scheme. So what we could do on the left, as you see on top, we have the NRZ symbol, 1 bit per symbol on the topmost, or you could go for, on the right side, you see on the same side with the NRZ, that here is the eye diagram, very good, nice eye that basically shows you that it's a good quality communication link. However, if we are able to sacrifice the signal to noise ratio a little bit, then what we could do at the expense of obviously the signal to noise ratio is transmit 2 bits per symbol. PAM4 allows us to do that. On the left, we see the PAM4 signaling how the signal will have, okay, 4 different levels. And on the right side, you see an eye that has, instead of 1 opening, it has 3 openings. Obviously, the signal to noise ratio is inferior as compared to the NRZ eye, but it is reasonably good and it could be processed, and it has been successfully shown to work in the real world. At the bottom, we could also transmit 3 bits per symbol. That will require PAM8, 8 levels, 2 to the power 3 is 8. And if we wanted a 4-bit per symbol, we would require 16 levels. The problem with PAM3 and PAM4, that the signal to noise ratio starts getting very, very messy, and it may be difficult to differentiate a 0 from a 1, or a symbol 000 from 001, and any of those 3 combinations. So at present, PAM4 is what mostly people are using in industry, in addition to our standard NRZ signaling scheme. So typically what we do is that we use a PAM4 IC, a PAM signal integrated chip, that mostly utilizes a Mach-Zehnder modulator. What the Mach-Zehnder modulator does, that based on certain phase angles associated with the Mach-Zehnder, it can take two parallel input bits, which each of them carry their own serial data, but 2 parallel input bits come in, okay, and they are combined together to create 4 different levels, and each of those 4 levels represent 2 bits, okay, depending on the combination 0001, 1011, and there are many different schemes. You could use the gray scheme, the gray coding scheme, or other schemes. It's up to you. In the end, irrespective of what coding scheme you are using, if you have the appropriate DSP, that will take care of the coding scheme. The only problem with the existing PAM4 ICs that we have, which use the Mach-Zehnder modulator, is that first of all these are additional system components. However, it is impossible to have, or based on our current technology, we don't know of any real ways to increase the throughput without adding additional components. So we are ready to pay for the additional components, but it is significantly more expensive. And on top of that, the power consumption is also almost doubled. And when you talk about hyper data centers, the heat removal is also a huge challenge. So what we need is a PAM4 signaling scheme that, instead of using the Mach-Zehnder modulator, that uses some other techniques which are less expensive and do not consume as much power. Okay, and if we could do that, we would be in a much better shape. Having said so, currently the PAM4 signal IC are made by multiple companies, and they have worked reasonably well, with the exception of the cost and the power. The ones made by Infi are probably the leading ones, but Semtech and Broadcom and others are probably also making. These three are the most common ones. So these do work, but there may be, or let me rephrase it, it may be better to have something that is less expensive and at the same time the power consumption is lower. So with that vision in mind, okay, we look for some other techniques. So the motivation for this particular technique comes from some of the earlier work that we did, that is called space division multiplexing or spatial domain multiplexing, which is a MIMO architecture, multiple input, multiple output architecture. And what it allowed us to do was to have multiple lasers of exactly the same wavelength launch into a fiber at different angles. And what that would do, instead of being a meridional ray flowing through the axis of the fiber, that will take a non-meridional path and they will follow a helical path inside the fiber, and they will appear at the output end. And if you took a screen projection of the output, it would look like concentric rings. So that is what we call space division multiplexing or spatial domain multiplexing in a single core fiber. There is another space division multiplexing that is in a multi-core fiber. No, this is different from that. We are talking about a single core fiber spatial domain multiplexing. So you take 3 laser sources, okay, or 2 laser sources, whatever you want. You transmit the different rays of light. They all come out at the receiver end or at the output end as concentric circles. Each of those circles correspond to a different laser source. So now at the output end, if I had a spatial multiplexer, I could go and take all these outputs to different detectors or different fibers, and I have basically invented a way that allows us spatial reuse of optical frequencies. However, if we want to make our life a little simpler, if we decide not to use the DMUX, the beam separator module at the output end, then what would happen? These 3 rings would basically fall on a single detector, and their energy would be simply added. If they do not interfere with each other, then their energies would simply add. And if the energies are added incoherently, then with all the 3 laser sources turned off, we have the lowest level. One level, let me call it level 0. And with only one source on, I have an output at the detector that is level 1. And assuming again that all the 3 channels have exactly the same power, then when I have 2 of these sources on, then I have my level 2. And finally, when I have 3 of these sources on, the added intensity will give me the level 3. So level 0, all sources off. Level 1, all sources on. So I can create a 4-level signaling scheme based on these rings, okay, and I could make them travel separately. Or if spatial multiplexing is not the goal, I don't care whether they interfere with, they travel on the same spaces or different spaces. So what SDM allows us, multiple input and multiple output MIMOs structure that allowed us spatial reuse of optical frequency. It is independent of wavelength. The output comes at concentric donut-shaped rings, okay, and it allows efficient reuse of the space in the fiber core. It carries OAM and can support TDM and WDM, but that is not the subject over here. But to be very quick, output angle is related to the input angle, and it can allow multiple data rates, multiple terabits of data rates. But I could also use the same technology to support PAM4. Let's go to our next slide to look into that, how we could do that. Okay, so if we go and look into it, let us say that I have two input bits. They are in parallel. One of them I call LSB and the other one I call MSB, the least significant bit and the most significant bit. And to make our life simpler, let's turn off or disable the gray mapping. It is possible to do that, but to keep the life simple and make the explanation easier, let's turn off the gray mapping. So when both the least significant bit LSB and the most significant bit MSB, both of those are 0, the PAM4 level when combined together, the output would be 0. Okay. And my binary level, that 0 will represent a 0, 0 output as shown on the left hand of the regular PAM4 signal, that 0, 0 level over there. When only the least significant bit is on, then obviously I'll get, and the most significant bit is off, I'll get a 0, 1. Okay, that is shown by the 0, 1 level on the regular PAM4 signal. And again, as mentioned earlier, we have disabled gray mapping over here. Okay, and in the third case, if my most significant bit is on and my least significant bit is off, then my level 2 is there that will correspond to a binary level 1, 0 as shown by the third level in the PAM4 signal. And when both of them are on, then what will we get? We'll get a PAM4 level 1, 1, okay, which will be corresponding to the PAM4 level 3 over there. So we could have two different laser sources to have that kind of a output over there. We need to create multiple outputs over there. So what we do is that for the LSB, what is the difference between LSB and MSB? If you take one laser source and keep it for LSB, and if you take two laser sources either in parallel or in series, we prefer to use them in series to save our power. If they are in series, then when you get the MSB signal comes to 1, both the laser diodes turn on at the same time. Okay, so you get the MSB bit, and that will give you the level 1, 0 over there, or the PAM4 level 2. So you have 3 laser sources. Okay, one of them for LSB and 2 of them working in tandem for MSB. That is what my basic architecture is. Very simple. Now, do we add extra cost due to the laser, and do we add extra power due to the laser? Indeed, we do. But if you go into silicon photonics, as Intel has shown now, that these laser diodes could be integrated directly onto the substrate or wafer level. If we have integrated the laser diode directly at the wafer, okay, then we are talking about very inexpensive $1 or $2 laser diodes, even probably less than that could be integrated. And if you put them in series, the total power addition is significantly lower. It may be adding another 10-15% as opposed to another 100% to make the total power go to 200. So we have a condition where MSB has 2 laser diodes 2 and 3, which are either both off at the same time or both on at the same time. That is what the MSB does. And LSB has only one laser diode. Now, we could send them through the fiber using my SDM architecture and get two rings, or if you don't care, you don't have to send them in a ring fashion. You can simply transport them separately. It's up to you. There are certain advantages that the ring architecture offers you, but that is not necessary. So based on that, the positioning of MSB and LSB, we create the PAM4 level 0, 1, 2, and 3, and associated with my 0, 1, 2, and 3 are my 0, 0, 0, 1, 1, 0, 1, 1 bit patterns. Okay, so basically what we do, we bypass the PAM4 Mach-Zehnder modulator, and we have a direct modulation scheme that could give us the output levels over at the photodetector. One more thing we got to pay attention to. In a standard laser or the standard PAM4 scheme, one laser diode is used to create four levels, right? 0, 1, 2, and 3. So look at my signal to noise ratio. My best case scenario, my signal level is A, or A by 3. My signal to noise ratio is A by 3, because the same laser diode, based on the I of a PAM4 signal, the power is divided into four levels or three different I's. If everything works perfectly, the signal to noise ratio is not A anymore. It is A by 3 if the total power at the beginning was A. However, in this modified PAM4 optical PAM4 signaling scheme, since we are using 3 laser diodes or 2 laser diodes or 1 laser diode for levels 1, 2, and 3, my total power is 3A. So my signal to noise ratio has improved, my cost has decreased, and my power is significantly lower than the power requirement of the PAM4 chip that is made by some of the leading companies as we have. So mathematically, you have two different inputs, okay, E1s and E2s, okay, or E2 could be double and E1 is half. Now here is the whole deal. All of these are operating at 10 to the power 18 and 14 and 15 hertz, and there's not a single photo detector that is available that can operate at 10 to the power 14 hertz. So if the phases are actually, or the wavelengths are actually interfering with each other at optical frequencies, no photo detector can detect. So the most important thing that we are down with is the visibility. And in this case, if there was a reflected beam, there could be some interference. However, in our case, the fiber, both the signals are going through or traversing the same fiber from some point A all the way to the end of the fiber. Do they really interfere with each other? The assumption is that they do, but in practice, they do not. And we will show that for them to be able to interfere, they got to be coherent. Exactly same wavelength from two different laser sources, it is very difficult to make them coherent. In general, they are not coherent, and as we will show you later with experimental results, that their input intensities will add. If you go to the final output at the right hand side, that I total is the sum of I1 plus I2, assuming I1 is equal to I2. They do not interfere, they add simply DC addition, the power levels add, it says a DC addition of the average powers, it is not an interference of light. And since it is not interference of light, only the DC powers are adding, we could have a modified PAM4 generated by having two laser diodes working together to have a level 2. One of them will give me level 1, none of them will give me a level 0, and 3 of them will give me my level 4. So we will show you experimentally that this is how it works. And later on, my colleague, Dr. Ahmad will also show you that the simulation tool also allows you to get to the same results. So, so to begin with, we take three 10 gigabit signals, okay, three signals, 1, 2 and 3, and we put them together through an optical fiber, combine them together as I showed you earlier on in my SDM or spatial or space domain multiplexing slide with SDM features, that they come into the fiber at certain angles. All of them I could detect individually, or if you combine them together, when all three are combined, each of them operating at 10 gigabits, okay, all three of them combined, now you get a 10 gigabaud signal that allows us with the PAM4 leveling 2 bits per symbol, 20 gigabits per symbol, okay, or 20 gigabits per baud. Now if I can, as you see on the left side, there are two 10 gigabits inputs. If I combine them together, that one MSB drives these two laser diodes and the LSB drives the one on the right, okay, then I have the LSB represented by this one, the combined effect of the ones on the left, they give me my MSB, and when they all go together, you get the PAM4I. Okay, this is a reasonable, and this is raw data without any signal processing whatsoever. So what we have effectively proven over there, as I was mentioning earlier on, that these two levels, or these two MSB and LSB, these two bits could be driven independent of each other, and then they are combined inside the fiber. They do not interfere, only their intensities are added at the photodetector, and with that we have the PAM4 signaling scheme available to us. This was result at 10 gigabit. Let's go to our next slide and we will be able to see at higher data rates as well. So initially, we tried the 10 gigabit at 1310 nanometers. We tried that at 850 nanometers as well. Okay, both of them at 10 gigabits per channel, MSB and LSB, okay, and the baud rate was because each of those channels were operating at 10 gigabit, okay, both MSB and LSB channels, the total came out to be 20 gigabits per second or 10 gigabaud per second. The eye diagram is reasonably good. Again, this is pure raw eye, no signal processing applied to it. At 850 nanometer, we see the same thing over here. Now the last slide, if you go and look at that, on the right side, what we have, we use again the same 1310 nanometer, but instead of using the 10 gigabit per channel, we used a QSFP, commercially available, made in China QSFPs, okay, and using those, okay, we combine them together and using not a state-of-the-art equipment, but we call it a simple checker from Gigalite, okay, that will drive all the other four lasers in the least expensive fashion, okay, probably $1,000 equipment, each of those. With that, when you drive them, you see 25 gigabit QSFP gives us the eye diagram that allows 50 gigabits per second or 25 gigabaud per second, 1310 nanometer, and over a distance of 1 kilometer. Now, most hyper data centers require lengths of 500 meters, typically at the most nothing exceeds 1 kilometer. So this kind of a PAM4 signaling could be used to push data in data centers at 50 gig. And if we use 50 gigabit per second QSFPs, we will be able to transport 100 gigabit per second per lane. The experimental data we have is only up to 25 gigabit per second per lane, leading to 50 gigabits per second total per lane. Why? because our QSFPs and our drivers were limited to, in the lab currently, to 25 gigabits. And you look at the OMAs and the ERs and RLMs, okay, they are also reasonably good. At 850, it was 0.78. You would prefer it to be about 0.8, but we can improve it or reduce the distance, or increase the coupling efficiency. Ideally, you want it to be about zero point 0.8, okay, but it is reasonably good, I believe, with the raw data. So, as I was telling, that with the raw data, we have reasonably good ones. And now, in the end, what you need to do is to get your zeros and ones. So there are clearly, if you go at the oscilloscope trace of those levels, you clearly see that there is 0, 1, 2, and 3 levels, or 1, 2, 3, and 4 distinct levels over there, each of them corresponding to 2 bits. So even at 20 gigabits, we have the same thing, and it is almost the same way at 50 gigabits after a distance of 1 kilometer. Okay, so what we have effectively shown here experimentally, that I can transmit a PAM4 signal over distances up to 1 kilometer using 3 laser sources that add incoherently without the use of the PAM4, dedicated PAM4 chips. All you need to have is just a small change into the circuitry, one laser diode for the LSB, two laser diodes working together either in parallel or series. I prefer series for power saving reasons, but either in parallel and series, and that will be forming the MSB, and then they will add, they will propagate through the other fiber incoherently, and they will add at the other photodetector to give you the amplitude modulation within the same pulse at 4 different levels, to call it pulse amplitude modulation 4 level, or PAM4. So here, if you see the combined PAM4 signal, again, the MSBs and the LSBs, okay, as you see that we can very clearly differentiate between the different levels. So what we have effectively shown, again, to summarize what I said in the previous slide, that MSB and LSBs of the PAM4 bits could be easily separated to produce the original bit pattern that we had. And as long as you have a one-to-one correspondence, you have a signal, a communication architecture that is working. I think our BERs are significantly better than what is acceptable in the industry. And our BER is e to the power minus 4. Industry at this point is operating at e to the power minus 3. Okay, so it is better than what, and that to keep in mind, we have the least expensive modulators for the different laser diodes, the from a device that was designed for a different purpose. It says as a checker that is primarily there to determine the quality of the QSFP alone. They are not synchronized. The signal could be improved significantly if we had the opportunity to synchronize them better. At this point, I'll hand over to my colleague, Mr. Dr. Ahmad, to go ahead and talk about the simulation procedures. Thank you.
Thanks very much, Professor Sayed, and hello again, everyone. Okay, now we're gonna talk about the simulation part, where Professor Sayed and his students used in their lab to simulate the system, the PAM4 signal generation and transmission as well. And in the project here in OptiSystem, basically the project layout, these are the list of the components used to build up the system. We start with the pseudo-random bit sequence generator here, which generates the 10 gigabit per second or 25 gigabit per second signal, and put it on a non-return to zero pulses format, and then directly modulate the laser. And then this is the least significant bit, and then the most significant bits is coming through the 2 laser diodes. As you see here, you have a different pseudo-random bit sequence generator, which passed it into a pulse generator into the 2 lasers, directly modulating 2 different lasers. Now the 3 lasers, as you see here in this slide, they are working at 850 nanometers. And then these lasers are combined and then transmitted through the optical fiber. In this scenario, we can control we're going to show you how to control the component parameters. And then after that, it's detected through a photodetector. And as the professor Said was saying, the power is added up and then detected. We have here a 3R regenerator to adjust the timing. And then eventually we look at the eye and the performance of the signal. Now in here it shows the produced eye. You can see the levels of the PAM4 signal. This is level 0, level 1, level 2, level 3. And if you go to OptiSystem now, I'm going to show you the setup in OptiSystem. So here, for example, the layout of the project. And this is the pseudo-random bit sequence component. So if you click at any component in this layout, you can set up the parameters. In here, we run the bit rate of the pseudo-random bit sequence generator at a global parameter. So if you click on the layout here, you'll set up, for example, bit rate here at 25 gigabit per second. So the pseudo-random bit sequence generator generates bits randomly at 25 gigabit per second. And now this is the least significant bit, 25 gigabit per second. 25 gigabit per second goes to the most significant bit. And then once you combine them and eventually run it through the fiber, here you're going to get the 25 gigabaud or the 50 gigabit per second signal, PAM signal. Now, the way how to set up the parameters, you can set up the parameters in every component by double click on it. And once you set it up, you can control the parameters in it. For example, here in the pulses, you can control the rise time, the fall time, and the bit size, and so on. In the lasers, which is right now, for example, as Professor Said was saying, he used 3 different cases. So you can control the wavelength of the laser. Then you control the power levels, you can control the extinction ratio, the line width of the laser. So all the actual parameter of the laser, you can plug it in the simulation here. You can set up, for example, overshoot or undershoot of due to the direct modulation. You can control the rise time, fall time, all these parameters in the laser. You can control it. You can control the side mode, suppression ratio. You can control relative intensity noise, if there's a chirp, polarization. So all these parameters, you can set it up. Once you set up these parameters for every laser, then you go, for example, to the other components. In the component here, then optical fiber, you can set up in the optical fiber component. You can adjust here the window to look at the parameters, and then you can set up the parameter wavelength. For example, we are using 850 nanometer here. You can change it to 1310 for different lasers, or 1550. You control the length of the fiber, transmission fiber, control the attenuation. You can set up the dispersion parameters. You can control the dispersion value, and then you can, depends on you can control the BMD as well. Nonlinearity, you can include nonlinearity in your calculation, and other parameters. You can set it up in the calculation to be able to simulate the actual fiber. And once you do that, you can do the same thing for the detector. You can control the responsivity. You can control the noise sources. You have different types of noise sources: thermal noise, shot noise. You have dark current. You have beat noise. All these types of noises. You can have certain frequency responses added up to the detector. So all these parameters, you can adjust it, and then eventually you can calculate the project once you set up. Now, the simulation process in OptiSystem, it's very simple. You can basically have you have here a component library where you have the default. If you double click on it, you have all these components available in OptiSystem in categorized in every category. For example, this category here for visualizers, you have different types of visualizers. You have optical, electrical, and compare types of visualizers. You can drag any component from here and place it in the layout, and then eventually you can connect it between components and set it up. Okay, so now in terms of the calculation, you have the calculate. Once you press on calculate, this project takes now very fast. It takes very few seconds to be done. Now, once calculation is done, you can go to any visualizer and double click on it, and then you see the eye diagrams and other parameters. Now, once you can, for example, you can change the wavelength of the lasers. Here we have 1310 nanometers, and the same scenario, you can do double click on it, you calculate, and then you look at the possible generated eye for the different configuration and different lasers. Here 1515 nanometer lasers. The same scenario, you can calculate. I did the pre-calculation first just to save time, and then you can look at the eye as well. Going back again to the presentation, if you change the data rates, and you can adjust the system to be able to do, for example, bit error rate calculation, and to be able to do bit error calculation to characterize the overall system. What we have a bit error rate test set here, where it generates randomly the bit sequences which passed into the PAM4 signal generator, and then after that it passes into an memory threshold detector here to decide about the levels. So in the decision detector level here, what's happened is you, based on what is received, you can decide, you put a threshold, and then you decide which level is received, and this PAM sequence decoder decide if the sequence is 00 or 01 or 10 or 11, and then we have a MATLAB code here as a MATLAB component added into OptiSystem, where separates the bits, the least significant bit from the most significant bit, and pass it back into the bit error rate tester, and there you get bit error rate of the sequence sended. Okay, so I'm gonna go back again to OptiSystem here to show you the calculation. So bit sequence generator, or the bit tester here, you can control the number of bits and the randomness. You can have the pseudo-random bit sequence. You can have external random bit sequence or internal random bit sequence. You have your user defined, so it can have flexibility to put the sequence required into your test set. And then if you double click on this configuration, this is the data which comes from the bit error rate tester, goes into this block here, which is, we call it subsystem. And this subsystem here, it has the pulses, which is null return to 0 pulses, and goes into the most significant bit in this section here, and the least significant bit goes into this section here, and then combined and transmitted through the fiber. In this case here, we transmitted through actually 3 kilometers of fiber at 1310. We put attenuation 0.3, 5 dB per kilometer. Dispersion is 16 picosecond per kilometer nanometer. And then after that, you pass into the detector. And after the detector, you go into the memory decision detector circuit. So memory decision circuit here component, you define the output amplitudes, which we have here, -3, -1, and 1 and 3. And this is the threshold levels, which is based on the eye opening. So you can adjust your threshold levels in here. And then once you set up these parameters, you can pass it into the PAM decoder here, where these levels received. So if you can look at these levels received, which is 00, it's at -3, 01 at -1, 10 at 1, and 11 at 3. So if you receive, for example, level -3, you code it 00. If you receive 3, you're going to code it 1-1 after this component. And then eventually the MATLAB code here, if you double click on it, this is a MATLAB component added in OptiSystem, which enables users to write their own code and communicate between MATLAB and OptiSystem, which is very flexible component. In this component, you can use MATLAB libraries as long as you have a certain structure of the signal. Now, if you need any details about any component, you just go to the help button here, and the help button will pop up a window. This window will show the component specification and theory behind it. So it can show you, for example, the structure of the signal in the MATLAB component and how to set the component. So this is very helpful resource in OptiSystem. And after you design you write your code, for example, in MATLAB, then this component basically will once you run the software, you can, for example, here have option to load MATLAB, for example, during the calculation. So once you do the setup here, the MATLAB, once you calculate, it's going to be loaded, and then the calculation, once it's done, eventually the MATLAB code would be executed, and the results of the MATLAB code in this scenario is separating the least significant bit from the most significant bit. And eventually, as you can see here, for example, if you look at the I, this is the received I after the transmission over the 3 kilometers of fiber, which we showed you in the OptiSystem in the subsystem here. Now, this is the this visualizer here. You can see the bits which is coming out of the bit test set here, and this is, for example, the bit. The visualizer shows you the received bits after separation from the least significant bit, and you can see there is a one-to-one match. As you see here, the bit error rate is 0, which means if you look at all these bits in here and the bits on the other from the sequence, you should have no errors in them. Now, the same scenario for the other significant bit. If you look at the bits in the most significant bit and the other bit here, the same sequence, you compare them, you're going to see exactly the same bit sequences at the output of the transmit, which means that the system, once you do the PAM signal generation using this novel scheme, it's possible to transmit data rates, as we said here in this example. It's running at 10 gigabit per second in this example, and then the baud would be 10 gigabaud over 3 kilometers of fiber, as we showed in this example. With this kind of signal here, if you can see, if you wanted to look at for example, the pulses, we have a component which is called optical time domain visualizers. You can place it wherever optical signal, for example, and you can look at the signal levels. Here we have the different levels of the PAM4 at 20 gigabit per second. The level 0 here, 0, 0, and then 0, 1, and 1, 0, and 1, 1. This is the I diagrams which we showed you before at 20 gigabit per second and 50 gigabit per second, generated using the schemes for using this kind of novel scheme of generating PAM signals. Okay, with this I conclude the presentation, and I'd like to acknowledge the work has been done by the student of Professor Sayed, Bilas Chaudhary. Is doing his PhD there, and I would like to thank my collaborator, Professor Sayed, as well. And at the end, if you'd like to have any question, you may direct it to OptiSystem support email, which is here, or myself. And you may also be able to communicate with Professor Sayed through his email, morshid@ee.fit.education. With this, thank you very much, and appreciate your listening to this webinar.